Hello, testing mic. Okay. Yeah. Hi everyone. This. Okay, I should probably switch that. But yeah. So I'm taking the camp meet for Centroid Decomposition and Auxillary trees. For everybody attending online, I hope that the quality and stuff is still the same. There's going to be some delay between like YouTube and whatever, so I'll try to just make sure it's fine, I guess. Uh, But yeah, for this meet, I'll sort of start by giving a rough overview of how I expect the meet to go. That doesn't imply that it's going to go like that, but I'm going to probably spend 80% of the time on centroid decomposition and 20% on auxiliary trees, because I sort of see auxiliary tree as like a nifty technique that you can use to like apply anything you know on trees, like on top of an auxiliary tree, and I'll sort of just cover it as that. But with centroid decomposition, I sort of want to cover the implementation and some problem solving part of it. And as a preface, I'll also mention that these techniques are both probably extremely unnecessary and you'll almost never find a problem on it. Uh, like at least, one thing you'll realize as you solve centroid problems is that like they all sort of have the same sort of vibe to it or the same sort of ideas, so it becomes pretty easy to recognize it. And like so you'll only find like like so in the past you'll find there were a lot more central problems than are asked like nowadays on CF and at Coder and stuff. But like you might see some extremely difficult ones where you have to take centroid specially and do stuff, but more or less you don't see them that often. But it's still a very powerful technique, and that's what I'll be starting with. Uh, the other thing with centroid is that I think a major part of the difficulty with centroid is that implementing centroid decomp is pretty difficult. Like at least there's many different ways to do it, and if you aren't using a good way, then it can make the implementation a lot more tougher than it has to be, a lot more constant heavy and stuff. So I'll be spending a reasonable amount of time on covering the implementation as well. Yeah, let's go. Oh, and yeah, so credits for the central decomposition part of the slides and the structure of this meet. A lot of credits to Tanuj Khattar. He took a meet sometime back on, I think, Coach Chef's ICBC camp. So if you want, you can also watch that if this isn't good enough. Um, yeah, what we'll be covering today is we'll start by spending a decent amount of time motivating central decomposition and why is it a thing, why did we come up with it, and to preface that you need to know what divide and conquer is and make sure like you get a good idea of how it is. The second thing is, of course, like okay, divide and conquer is cool, but how do you use it on trees? How can we sort of solve problems on trees with it? And finally, we'll figure out how to implement it, and then later we'll go check out some problems. And finally, I'll cover auxiliary tricks and show some problems on it. And if we have time, we'll also check out maybe like I won't go into depth in supernode trees, but I'll sort of give the gist or the idea behind what they are and how auxiliary trees can kind of work with square root decomposition to give you something cool. So that's fine with everyone, right? So yeah, let's start by motivating centroid decomposition as it is. For that, let's start with divide and conquer, right? So, what is divide and conquer? Okay, or a better way to put this, what is one divide and conquer algorithm that any CS grad student knows, like, or will learn within like a month of like starting to learn like BTech? Yeah, binary search as well, but I'd say more commonly merge sort. Like also because that's what I have slides for. But and like it also shows like a little more parts of what I want to cover. So we'll think about merge sort, and merge sort is a divide and conquer algorithm, but I still feel like usually like merge sort is just thought as like okay, we tried some shitty n square sorting algorithms, and now here's a cool n log n sorting algorithm. Uh, what Mozart is doing is pretty much just utilizing this broader framework of divide and conquer. And divide and conquer is basically like, I like to just think of it's basically just a framework that you can apply to solve a lot of different problems. And it makes solving a lot of very difficult problems a lot easier once you think about it as, splitting something into parts, solving each part separately, perhaps building a data structure out of each part, and then using those created data structures to solve the current state more efficiently. So, this is basically Mozart, right? So this is from Wikipedia. I hope the quality gets better. So I'll check for two things. One, I want to see if. So you guys can't read anything, right? Here? Yeah. Sritet FX hotspot. Give better internet. Uh, this thing where you take an array and then you split it up into pieces, and then you combine them together after building a sort of data structure on each individual part, right? So what do you do in the top half? You just split it in half. You get two parts. And to solve that, if you look at the leaf layer, which is okay, that's much better. So yeah, if you look at the leaf layer over here, what you're essentially doing is you're taking two sorted parts, and individual elements are by themselves sorted. So you have a linear time algorithm to merge two sorted lists, right? So essentially, the data structure that this level of recursion returns is sorted lists of size 2 or 1, right? Like it gives you smaller sorted lists, and that's the data structure you're returning from that level of recursion. And at the top, and at this level over here, you're essentially able to combine this return data structure in a fast time, right? In linear time, essentially, right? That's the whole idea behind merge sort. But this generic framework of like dividing, solve separate halves, and then once you solve them, return some sort of information about these two halves to the higher level of recursion that call these two halves, and then use that to solve the current layer. That framework is essentially very useful to solve problems. So let's start by overkilling like a very easy problem with divide and conquer. Uh, Hoping links. Okay, that sucks. Yeah, yeah, that's the problem. So it's a fairly simple problem. Let's start by solving this with, okay, let's just try to solve this, right? So you're initially given an array of n integers, and you have learned about partial sums, which is basically just prefix sums, and you can calculate the sum of elements on any segment of the array first, which is fine. So, like all the bullshit aside, you basically want to count the number of segments in the array with sum less than t, right? This is what you want to solve. You want to calculate the number of segments in the array with sum less than t. So, I mean, just go for it. How would you solve this problem? You don't need to like come up with the centroid approach. I mean, sorry, have I been saying centroid the entire time? The divide and conquer approach for it, like just come up with whatever solution you have. Store prefix sums in a multiset and do binary search. Uh, yeah, yeah. So you essentially for yeah, yeah. So yeah. So given some array like this, what you essentially want to do is you can just store the prefix sum, like you have all the prefix sums value p0, p1, p2. You have all the prefix sums computed till pn, and when you are at some position I, like you can just iterate linearly from left to right, and when you're at some position I, let's say you're at pi, you know that you're looking for values of px such that px minus pi minus 1, what is the condition? Is less than t, right? Yeah. No. Is less than t. You're basically looking to satisfy this condition. So as you're iterating from left to right, just remove all the people like before you, and yeah, you can just rearrange it so that you're looking for px less than t plus pi minus 1. So you essentially get this equation, and you can just count it. Um, like uh, like you need an ordered set, right? Yeah, you need an ordered set, or it's probably worse, but yeah, like I mean, some extremely constant factor heavy stuff, or the easiest would just be using a Fenwick tree. Like you can, at the values small, like something you can probably compress them, and yeah, like even if they're kind of big, you can compress them and do the same thing with segment trees or whatever. But okay, fine, that's one solution for it. Let's try to solve the same problem using just divide and conquer now, right? So the same problem, but let's not do this, and let's try to solve it by somehow just splitting things in half. Like it's very unnecessary, but I think it'll sort of get the idea across. So let's just say you are going to split it up into this half. Um, whatever, right? Like, I think it's a horrible drawing. One sec. How does that happen, bro? Fine. Yeah, whatever. Essentially, you're basically just splitting stuff up. That's a terrible drawing, but uh, yeah. How can you sort of use DNC on it, right? So the two properties of like divide and conquer that you want to do is that, like, when you are solving some region, right, you're splitting the array into parts, just like with Mozart. Like you're going to solve like if this is your mid, you're going to solve L to mid separately and mid plus 1 to R separately, right? That's how you're. That's how the problem is defined. So the result of like your function is, let's say, f, and you call f in some range L to R, right? So when you call f L to R, similar to merge sort, you want to compute the answer for the entire range LR, and then to the level of recursion that called you, the parent that called you, you want to return some sort of usable information that the parent can use to compute the details faster, right? So uh, when you're at the bottommost level, right? Let's just think about it at the leaf level over here. What is you're basically going to have f of I comma I, right? What is f of I comma I supposed to return? Like, what is it supposed to do? Like, just tell me what the answer is for f of I comma I, right? The problem is to count the number of subarrays such that sorry. Yeah, you basically just want to say, is element a of I less than t or not, right? If it is, you're going to return 1, otherwise you're going to return 0, right? Because your function is just counting. It's the same as the problem, right? For given a range LR, count the number of subarrays in that range LR which which have sum less than t, right? So when you're looking at the range I to I, you're basically just going to say, okay, for I to I just need to check there's only one subarray. Is A of I less than t or not? That's all you really care about. And like I said, you need to give some sort of usable information to the above layer. But given that you're only a singleton element, like you're just AFI, like you're just going to return AFI. So let's look at the layer above that to sort of see what better structure you can kind of give the guy above you, right? So, yeah, essentially, yeah. The data structure you want to give is the prefix and suffix sums, because so you want to sum up FFI across. Yeah, you want to basically yeah. So let's call this A to yeah. Let's call this range A to B, I guess, right? So we're calling that range A to B. So what is f of A to B going to be equal to, right? F of A to B is going to be, first of all, equal to f of A to A plus f of B to B, right? These are all the subarrays that were in the left half and the right half. They're also going to obviously be a part of U, right? Because they are completely overlapped children of U, so they're going to be a part of U. So now when you're counting the excess stuff, what is the excess, right? Excess is going to be stuff that has the left endpoint, right? If you look at the subarrays that you're looking at, the left endpoint has to be in the left half. The left endpoint has to be in the left half, right? In the range A to mid, and the right endpoint has to be in the range mid plus 1 to B. Like, I mean, this is a 2-element thing, but essentially that's what you care about, right? That's only those specific subarrays are what you care about, because any other subarray would overcount, or if you don't count it, it'll undercount, right? So to count everything, you want to look for these things. So is that fine with everyone? Like, that's the excess you need to count, right? So okay, so when you're iterating on this side, right, like just the left half, when you're iterating on the left half, you are obviously checking that, okay, so let's make a bigger left half and right half, because I think it'll make it easier to see. So this is the left half, fine. How? Okay, so this is the left half, and you have some A0 here, or let's call this, is this suffix? Yeah, this is suffix sum. I mean, fine. That's suffix 1, suffix S2. So you keep computing this. So if the left endpoint is at this element, at what all right endpoints is our sum going to be equal to, is our sum going to be less than t? How do you find that fast, right? If you had all the prefix sums computed from this guy, right, from the right half, if you had all the prefix sums computed, you can just again get that equation like this. You are at some S of I. S of I plus P of X has to be less than T. You can again rearrange that to just say you're looking for P of X such that P of X is less than T minus S of I, right? One nice thing here is that you can just compute all of these prefix sums beforehand. You can sort them, and then you can just lower bound, upper bound query. It's still going to be log square of n, but it's still like very much better constant factor. Like, probably not better than Fenwick, but like, fine. It's just one way to solve this problem. The goal of me showing this technique was just to show that you can solve problems like this using just normal divide and conquer ideas, right? So divide and conquer is fairly powerful, and we'll look at another problem. First of all, let everybody kind of understand how I use DNC to solve this problem. right? It was absolutely unnecessary to use divide and conquer. But did you sort of get the idea of what I meant by solve like divide it into separate halves, solve one half, solve the other half, and then return some usable information in some data structure? Here we saw that returning prefix and suffix sums was very efficient. I mean, that's what we needed to solve the problem fast, right? So what is the time? So also to reason about the time complexity, I think the easiest way is just Master's formula, or the easier way, like if you want the intuitive way to look at it, just look at the recursion tree. You will have log n levels for this recursion always, right? You will have, I'm always dividing at the midpoint, so I'll have log n levels. At each level, I'm iterating on each element exactly once. And for each of those elements that I'm iterating on, I do one binary search query. So it's going to be n log square n, somewhere around there, right? So that's how you reason about the time complexity of this, and that's how you solve this problem with divide and conquer. Is that fine with everyone? If anyone has issues just let me know. Cool. So next, let's take a look at this problem. I probably won't explain this too much in detail, but and I also hope I remember the problem. But you're given n integers, and the problem is fairly simple. Just calculate the number of calculate the maximum numbness over all possible subarrays, and the maximum numbness of a subarray is defined as the max of AL to AR XOR with all the elements in the range AL to AR. So the problem is clear with everyone, right? Good. Now I hope I can solve it on the spot. But let's see. Okay, let's just try to solve this, right? So let's try to solve this with divide and conquer, because that's essentially the solution to this problem. I mean, I think there's some other solutions, but whatever, right? So let's suppose you know the answer to L to mid and mid plus 1 to R like normal. So you have computed the halves answers. You now care about subarrays that specifically, let me erase this stuff. So yeah, you specifically care about subarrays that uh, cross the range, and let's say that's the midpoint. So how the okay. So what is the function again? The function is the maximum of AL to AR XORed with AL A plus 1, the XOR of all subarrays that end there. Okay, fine. So for this function, so another thing to notice is that XOR is invertible essentially. So I could just say this is the same as I say 1 second. So the maximum. Okay, let's solve this for cases where the maximum element comes from the left side. So I'm going to care only about situations where the maximum element is from the left hand half of it. So let's say that this guy is the max element. So if he is the max element, let's call him AI. Then I can consider all elements on the right hand side whose values are less than AI, right? That's everybody who I can consider from the right half. And now I know that because I'm fixing AI, I'm fixing some prefix. So I know the value of that prefix. So I know the value of the prefix, like the x, like okay. There's two parts. Okay, there's two parts to this problem, right? There's max of AL to AR, and then there's the XOR of that subarray, right? So when I'm iterating left hand, like when I'm iterating towards the left here, I'm going from mid to left, right? So when I do this iteration, when I'm at some element over here, I know that I know this XOR for sure, right? Like I know that this is going to be a part of my XOR regardless because I'm looking for endpoints in the right half. So fine, that's a constant. I mean, yeah, for this computation, it's a constant, and I'm fixing AI as my maximum element. That means that on the right hand side, I can use all elements that have, like I can use all endpoints whose prefixes, whose prefix max does not cross AI, right? So that means I can store them in a data structure. It's sort of like I'm doing a sweep line type thing. And is everyone familiar with this problem where given a set of numbers given a set of numbers, right? Find the maximum XOR with a queried number. Do you guys know how to solve this problem? Yeah, the try problem. Like is okay. How many people don't know what that means? Fine. Fair enough. So you guys know what a try is, right? Like a try is basically just data structure where you store things by. Wait, I'll just give an example. I think, like given the string 0, 0, 1, 1, 0, and 1, 0, 1, 0, 1, and 0, 1, 1, 0, you would basically store it as 0, 0, 1. Oh, yeah, 0, 0, 1, 1, 0. Wait, no, this is bad. So 0, 1, and the 0 extends here because we're inserting the first guy, right? So 0, 0. Then again you follow this. The 1 extends this time because the next element is 1. And finally we extend into a 0, right? That's how you insert the first string. To insert the second string, you start from here. 0, 1. The 1 extends on to 0, 1, and from there to a finishing 1. And for the second string, you go here, and this one will extend. Essentially, we sort of know what the try is, right? That's the try data structure. So given a set of strings in my try, I'm asking a question, I'm giving you an input value. The input value is some value, let's say y, right? Find the maximum element in this try, in the set of numbers I've stored in the try that has the maximum XOR value with y, right? Because powers of 2 is greedy, right? Like if you can set the highest bit of like, so you're looking for some mystery value x in the try such that x XOR y is maximum, right? You're looking for this to be maximum. So how do you do this, right? Like because you can solve this greedily. If you can set the highest bit of this result to 1, you always want to do that, right? So you have the string y. Let's say y is 1, 0, 0, 1, 0, right? So the first bit of y is 1. So you want to try to make the highest power of 2 that you have, you want to make it equal to 1 greedily, right? Like it's optimal to always make that 1. So what do you need to make it 1? You need 0. So in your try, you just cut off everything there. You don't care about it. You just look at 0. So you go into this section. And then when you're in this section, you're going to look at the next thing. It's 0. You want the next, you want the next digit to be greedily 1, right? You want the value of x to be 1. So you look at the try and you ask, is there a person in my set of strings who has 1 there? And then you see that, okay, there is 1 string. So you look at the 1 and you go there. Now again, you need a 1, right, to make it greedily big. And you realize, okay, that's also there because this, like if you look at this string, this is giving, oops, this is pretty much giving you exactly what you want. But then over here, you again want a 0 over here. But in your try, there's nothing. There's no string from that point onwards which gives you the 0, right? So you just can't take a 0, so you must take a 1. It's a binary string. There's only 2 options. So you're forced to take the other option, go into the other section. So repeat this and you can solve this in log n time, right? So that's basically what that subproblem is. But essentially, the idea with this problem, right? So like I said, what you can do is you can sort of do this structure where I said, okay, you care about counting all the subarrays that satisfy, like, okay, you care about finding this answer of max AL to AR XOR the AL to AR XOR for that range, right? So how do you do that? So let's say the maximum element comes from the left side, right? So you're iterating on each guy and you're saying, okay, this guy is the max element, right? So first of all, can even be the max element? If there is an element aj in the left half such that aj is greater than ai can't be the max element. Just skip it. You don't care. So you first find an AI such that it is the biggest element in this suffix, right? AI needs to be the maximum guy in this range. So AI is max in this range. Fine. So now on the right side, and remember when I go left hand, this value of AI max keeps increasing monotonically, right? So what does that imply? That on the right side, you can insert into a try in log n, right? Like the length of the binary string is like log of n. So insertion into the try is the length of the string. Because the bit string is of length log n, insertion into the try is log n. So on the right side, you insert all elements such that their value is less than the value of AI you've picked so far. Does that make sense? So now you have some try data structure on the right side, which contains all the possible prefixes that you could have picked on the right side. So now you know that AI is the maximum, he's the max value. You know this suffix XOR, and you're just looking. So this is your query string, right? This becomes your query string Y, and you're just looking for the maximum value X in this try that gives you the max XOR for this combination of AI and suffix XOR, right? So this problem is essentially, it's still sort of extending divide and conquer what we did on the previous problem, but now we have thrown in the try, we have thrown in doing this in sorted order, and that's basically it. That's basically a 2400 problem solved, right? Sorry, what? Huh. Okay. Oh, my bad. No, that's my bad. Sorry. You don't skip AI if you find a AJ in that suffix. You just you consider that also. Yeah, my bad. Yeah, you're right. Thanks. Yeah. You don't skip it. Yeah, that's my bad. Yeah, sorry. So essentially, for you do it for every element. You just consider the prefix, the suffix max. Sorry, you just consider the suffix max and query that. Right. Makes sense. Thanks. So that is basically that for the left side. Do the same thing for the right side while computing the try for the left-hand side. And you've basically accounted for all possible subarrays. You're just trying to find the maximum value. Keep maxing this in your divide and conquer, and you'll eventually find the correct answer. Right? That basically solves this entire problem. Cool. So before we move on to doing this for trees, is everybody sort of comfortable with divide and conquer? If that is done, Centroid is relatively simple. It's a cool construction, and that's basically that. So if people so maybe the second problem, comfortably numb, is a little more involved, as in you need to know the try sub problem. You need to know like there's some sweep line type stuff. But is everybody sort of comfortable with that? Okay, and I will also check YouTube chat because I haven't been checking that. Hello, Adarsh. But yeah, fine. So yeah, that's basically that. Cool. So now let's try to. So the whole point of me trying to explain what divide and conquer does is because it's a very powerful technique, like I mentioned. You can solve a lot of hard problems with it. And previously, well, maybe not for people attending online, but previously in IIIT we had some meets about Euler tour and HLD. With Euler tour and HLD, the whole idea was that we have segment trees, which are these beautiful data structures which do range query of any like associative function on a contiguous subarray. On a contiguous array, you can query any interval LR in logarithmic time, right? They're wonderful data structures, and you sort of want to extend their same power to solving sub-tree problems and path problems on a tree. That's why we came up with these cool ways to linearize the tree to an array. So we sort of linearize the tree to an array to create ETT and the HLD structure, and then you could solve those problems fast. So with this meet, we want to sort of try to introduce divide and conquer to a tree, right? And probably spend too much time on divide and conquer, but I think it's worth it. So the whole point here is we want to sort of introduce the whole concept of divide and conquer on a tree. So with an array, it was sort of very easy to do it because it's a midpoint, right? It's very easy and efficient to think about it, very easy to code it up, because all your function cares about are the endpoints of the array that it's solving it on, right? Given LR, right? So that's just easy, right? L plus R by 2 or L plus R minus L by 2, however you want to write it. That'll give you your midpoint. Solve L to mid, solve mid plus 1 to R, do something. It's all very linear, it's all very nice to code, very neat, etc. It's not that easy to think about on a tree. How do you even like split a tree in half, right? Like, what's the notion of half on a tree? Like, half was important for divide and conquer because we wanted like that. We wanted to have logarithmic depth of recursion, right? We wanted the recursion depth to be logarithmic. But like, by the way, like for divide and conquer, you can split unevenly. There are problems where one half requires an uneven split, or maybe you split on something different and then you do like small to large or something to like make it efficient. But like most of the times, you care about splitting evenly so that you get the logarithmic depth. We'll just care about the simple DNC problems. So how do you do it in a tree? Don't tell me centroid. Tell me something else. Like, what are other things that you could consider to split a tree on? I mean, personally, I only can think of one other famous point on a tree type thing. Yeah, the center, right? Like, so how many people here know what the center of a tree is? I'm disappointed. How? Huh? Yeah, the midpoint of the diameter. So the center of the tree is basically a node such that. So okay, everybody, is there anybody who doesn't know what the diameter is? Cool. The diameter of the tree is basically, just in case, the diameter of the tree is the longest path on a tree between any two pair of vertices, right? The longest length path between any two pair of vertices on the tree. So what is the center? The center is a vertex such that it has the maximum distance to any other vertex from the center is minimized over all possible pairs of choices for the center, right? So you're guaranteed that if you are at this, if one of the vertices is the center, the maximum distance to any other vertex is minimized, right? One way to find the center is that it's always like if you take the diameter of a tree, like take a tree with a diameter like that. Like that node right there is going to be the center, right? Like you can have other things, I don't care, like fine. So that is the center of the tree because the maximum distance from that vertex to all other vertices is the minimum, right? Like if I pick any other vertex, it's not going to work. So the center is actually not a bad idea to consider doing decomposition on. And like before I even ask about splitting, what is decomposition? So what I mean when I say decomposition is take the tree, the same idea as with the array, like pick some cool vertex. Like let's say we're picking the center right now, and let's just remove it from the tree, right? If I remove a vertex from the tree, it's going to split that tree into a forest, right? A forest is a collection of trees, like disconnected trees, basically, right? So if I remove that, I get two trees. I need not necessarily get exactly two. I could have another thing connected over there, in which case it becomes, I get three trees from that. So, decomposition is basically this idea where you take some vertex, remove that from the tree. You are now left with a few other trees. You're left with that tree, you're left with this tree, and you're left with this tree, right? And now your idea, like, okay, you might not have two halves like with an array. Now you have three halves. You repeat the same procedure on these trees, right? You got some T1, you got some T2, you got some T3, right? You want to perform the same, like, find the center vertex and split procedure on these guys also, right? Like, let's say it's probably that. How does it? Okay. You get some tree inside. You want to recursively keep doing it. Pick a good vertex to do the split on, and break the tree into a forest over there, and then recursively solve that, right? That's the whole idea here, and I'll maybe like draw the inner ones in a different color to make it a little easier. Like I hope that's the center, by the way. Like I'm not thinking too much, just fine. Right. So the yellow layer is the first layer of my recursion, right? The yellow is the first layer, and then the green is the next layer of recursion, right? The same ideas would divide and conquer, but we're splitting trees now, right? So, okay, can anybody give me a bound? Okay, I mean, that's too much. Like, what do you think would be the bound if I pick the center? Like, what do you think it would be? Like, at the worst case, how many layers of recursion would I end up in? Like, can you come up with any case for it as well? Like, I tried for a bit as well. Like, I thought I had some construction, but I don't think that's correct anymore. So I'll just ditch that. But there is one other construction. This is, I think, Dorijanko, hope that's how you pronounce his name. He posted this on AC some time back. But this is a construction, right? So you have even length chains. And notice what. Right, you have even length chains like this. The diameter is always going to end up being the biggest two length chains. The the center will end up being like somewhere here, I think, and this portion of the tree, like you'll still keep doing it, and this would give you worst case root n, right? Because like you're essentially going like 2, 4, 6, 8. You can like given someone you can do this sort of like root roughly like a little more than the root n, but like somewhere around there, right? Like, does the construction kind of make sense? Like, why this would force root and depth? Like, on the first time you try the decomposition, the diameter is going to basically be like on this, and the diameter is going to be somewhere over there, I think, right? So when it's is that maybe even the node above that, I think, but yeah, essentially, okay, you cut off this part now, and the next diameter is basically going to be somewhere there, probably that guy, and then for each chain you're basically going to end up doing this decomposition. And like I said, you can have of the order like root n type chains, right? So like personally I feel like a decent bound on center decomposition is root n. Like I tried proving, I couldn't come up with like a very easy, I mean, yeah, it wasn't very obvious at least to like prove that it is under root n, but I feel like it's root n probably just because of the fact that the diameter is getting halved and you can make some claims using it. But like regardless, we want something faster than center, which is why we have the centroid, right? Uh, you can sort of prove that give like if you do the same decomposition process, but while picking that special vertex as the centroid, the recursion depth will always be log n, right? So what is a centroid? The centroid of a tree is a vertex such that its removal will split the tree into a forest of trees where each of the resulting trees contains no more than n by 2 nodes. Okay? You have a tree with n nodes. I claim that there exists some vertex, right? Or if you don't want to think about it in terms of removal, like there is some vertex in this tree such that if I root it at that vertex, okay, I'm rooting the tree at that particular vertex, none of the resulting subtrees will contain more than n by 2 vertices. It can contain equal to but not more than n by 2 vertices. Fine. You can prove that this like a vertex like this always exists in a tree. Fine. The proof is sort of also how you find it. So I mean, if you just intuitively try to do this, let's say this is your tree, right? 1, 2, 3, 4, 7 vertices, right? So there's 7 vertices in this tree. Like let's say you start at vertex 8, right? So you're at this guy, and you basically are asking, okay, where is you're a centroid finding algorithm. You pick a random vertex. It happens to be vertex 8. So your question is, you compute subtree sizes, right? You have computed, you know the subtree size of each vertex in advance. You know that, okay, when is 8 a centroid? if none of the subtrees have size greater than n by 2, right? So, I mean, let's add a vertex, I guess. So, 8 greater than n by 2, right? Yeah, fine. Let's just add like 2 vertices over there. So that's going to be 9 vertices in total. I don't want anybody to have more than like greater than. I don't want anybody to have greater than equal to 5 nodes. And you will notice that this subtree, we'll just write down the subtree sizes. So this guy has subtree size 5, 1, 1, 1, and this guy obviously has subtree size 9, right? So, okay, you're at a vertex, and he has subtree. So you look at all of his children. Okay, two cases. If none of the children have a subtree size greater than n by 2, you're done. That guy is the centroid, right? You've found the centroid by random luck. You've just found the centroid. If none of the vertices, none of his children have a subtree size greater than n by 2. Let's suppose that's not the case. He is not the centroid. That means there must exist at least one child with subtree size greater than n by 2, right? It's also true that if there is at least one child with subtree size greater than n by 2, there is at most one child with subtree size greater than n by 2, because one child is n by 2 already. If somebody else is greater than n by 2, that means you have more than n nodes. That's not possible. So you will have exactly one node. There must exist exactly one adjacent subtree with greater than n by 2 nodes, right? So I claim that the centroid must exist in his subtree, because remember, he has greater than n by 2 nodes in him, right? So me, who started at this vertex 9 over here, I'm going to move from 9 to 5, because the centroid is going to exist in that subtree. Because the parent part, right? Like once I move into the subtree, the nodes above me are going to be less than n by 2 always, because of the fact that I am greater than n by 2. Because my subtree size, the node that I moved to, has size greater than n by 2. The outside, the parent that I came from, everything in the parent part of it is going to have subtree size less than n by 2. So I just need to check all the vertices in his subtree, right? Does that make sense, the centroid finding algorithm? It's extremely simple. The proof for the existence of the centroid is basically the algorithm for finding the centroid also. If anybody has any doubts on how you find the centroid in linear time, just ask me now. Cool. The code is like extremely simple. If you're not comfortable with lambda functions, just it's a DFS with like a vertex u and a parent v. That's it, right? Ignore all the function intent bullshit. It's just void get centroid and those arguments. Fine. That's basically the DFS. All I'm doing is okay. Like this is part of the centroid code itself, so there's some more complex shit. But just you're iterating on all vertices over there, and like the all you care about is this condition, like just that. You're basically going to check if there is any child with size greater than n by 2. If there is, then return centroid. Otherwise, return u. If no child had it, just return u. Extremely clean, extremely simple code. I mean, not clean at all, like for what centroid finding should be. But yeah, that's it, right? Simple enough. Cool. So the whole idea with centroid decomposition is basically we want to write this recursive function called decompose, where you pick a centroid, and where you're given some tree, you find the centroid, you now delete all the edges from the centroid to all other vertices in that tree, right? And then you decompose you get a bunch of new trees, a bunch of forests, and then you recursively call this decompose function on them. Fine. That's the algorithmic way of looking at centroid decomposition. I'll sort of give you a picture of it to get a better idea of it. So here, the centroid is sort of colored. It's easier to see, hopefully, for everyone. This is the starting node, right? So let's start with this guy. So I mean, visually, you can sort of agree with me that the node, I think 8 is the centroid of that entire tree, right? So now we have ended up getting 2 halves, right? So the half over here, I'll call this white look visible, no? Yeah, let's call this T1, and let's call this T2, okay? You get 2 different halves, fine? Once you have these 2 different halves, we look at the centroid of T1 and T2. What is the centroid of T1? Huh? Yeah, like let other people also. Like, what is the centroid of T1? Huh? Sorry? Fine, it's 9, right? Okay, fine, yeah, fine. Obvious, but this interaction. So, yeah, it's 9. What's the centroid of T2? Also colored in the same color so that you can identify it. 2, right? So you now break all these. So once you pick the centroid of T1, you get 2 trees in T1. So let's call this T1. Let's call this guy T12, and let's call T11, and let's call this T12, right? But look at the right. With T2, you get a bunch. You get a lot more trees. You get T21, T22, T23, and T24, right? You get a lot more trees. Now in T21, the centroid is this time highlighted in blue. You break it over there, break it over here, over there, and you get some stuff, right? So the first question, what node is the root of my centroid tree? Where did I start this whole decomposition process? So, by the way, okay, it's not here. The whole point of the centroid decomposition thing is to construct a new tree. Okay, you're constructing something that's called as a centroid tree, and in the centroid tree, there's going to be an edge from the. Okay, you broke a centroid over there. It's going to be connected to the centroids of all the forest trees. Okay, that's the construction we have. So, constructing a tree like that, what's the root of the centroid tree? Right, it's the red node. It's going to be node 8. Right, it's this guy. So another question, how many children node would node 8 have in the centroid tree? Huh? Can everybody agree on that? How many children can the children nodes would node 8 have in the centroid tree? Chance. Right, you would have exactly 2 children because red is going to connect to the centroid over there and the centroid over there, right? So you broke it into a forest, and node and the centroid at the parent level is going to connect to the centroid of all the trees in that forest that you just created. So you'll have 2. So let's look at what the centroid tree actually looks like. This is the tree you've constructed, right? So for just to make to clear all your confusions off, make sure you understand this well. This is what happens. Don't try to draw any relation between the centroid tree and the actual tree. An edge existing in the centroid tree does not imply that the edge exists in the actual tree. An edge existing in the actual tree does not imply that an edge exists in the centroid tree. It's a completely different tree. You build this tree for other purposes, which I'll explain later. But try your best to not do when you're solving, especially in the early stages, don't try to do some sort of DFS on the actual tree and sort of remember that, oh, these 2 nodes are connected in the centroid tree as well. It might not be true. By connected, I mean directly connected, obviously. So you pick the first level centroid, right? And does that image make sense? Just take a moment to understand that construction. Red is going to connect to the centroids of T1 and T2, green and green. Green is going to connect to all the blue centroids, and all the blue centroids are going to connect to all the gray centroids, right? So okay, I'm just going to ask you guys, what simple, just keep it simple. What do you think are some cool properties of the centroid tree? Huh? More stupider properties. This construction is always connected. We'll start with that. So yeah, obviously, because you're okay, more importantly, more than connected, it contains all the nodes, and all the nodes are connected in the form of a tree, right? So just based off of construction, you never put a cyclic edge, right? You always recurse downward. It's a recursion tree, so you don't have any cyclic edges. All the edges you added are from the parent level to the child level. So it's a tree structure. It contains all the nodes because at some level you would have come across singleton nodes, and that's where your recursion would stop. So you have the central tree contains all the nodes, and it's connected, and it's a tree. right? That much is obvious. Okay, what's the second cool property that you think about it, that you can say about it? Height is log n. Yeah, fine. So why is the height log n? Why would you have at most 2, 3? Yes. Yeah. Yeah. Yep. Yeah. Exactly that. Is basically this, right? At each step, when you pick that centroid to decompose, when you remove that centroid, the next level you get a forest of trees. Each of these trees are going to have size less than n by 2 of the previous tree, right? That's the whole reason why you can probably say that the height of this tree will always be log n, right? That's the cool property about this tree, that the height of this tree will always be log n, and the proof for it makes sense, right? Because you pick the centroid, the next level, all those trees will have size n by 2. Eventually, you're just halving, you'll eventually end up, like worst case, you can have an array and then you'll end up with the same. Yeah, I guess worst case is probably an array and you'll have the same divide and conquer type array, like array DNC structure. Fine. Is everybody following me till now? Cool. Yeah, now we'll come across the very cool properties, and this is basically everything that you need to know about the centroid tree. Like everything till now is sort of motivation, something, basic structure stuff. This is basically going to be the one singular property, if that comes to good quality, that makes the centroid tree the centroid tree. I'll also just check this thing once. Give me a second. So, yep. Like, if just okay, everybody can read that, right? Yeah, cool. If it's rendered, then fine. So, pick any two arbitrary vertices A and B, right? In the original tree, we're talking about the original tree. My God, man, Jitsi. Yeah. So, in the original tree, you can always break it down into a path A to C and C to B, where C is the LCA in the centroid tree. I'm talking about two different trees here. Keep that in mind. Any path in the original tree, A to B, I can break it up. So find the centroid. Okay. In the centroid tree, like just think about the construction of the centroid tree. At some point, I removed a vertex, right? I removed a centroid during the construction of the centroid tree. I removed some centroid. I decomposed it along that centroid, and that centroid split vertex A and vertex B into two separate trees, right? Huh? Same? Eventually, at some point, right? Like, not, it might not happen at the root, but eventually, as I keep decomposing along the centroid, there must be some vertex I remove such that I've split vertex A and vertex B into two disconnected for trees, right? So that vertex is going to be the LCA in the centroid tree, right? You can agree on that. The first vertex I remove such that it splits them will be the LCA in the centroid tree, and that's basically also the proof for the first statement. I can always basically just say that any vertex A to B, right? So give me any two random vertices in the original tree. Like let's screw it. Let's just pick vertex 1 and let's pick vertex. Let's pick vertex 5, right? So there is some. Okay, look at vertex 1 and vertex 5 in this tree. 1 and 5, right? The LCA is 2, right? Because the first centroid at which they were split is vertex 2, right? Along this decomposition process. Does that make sense? Right? My whole claim is that given any path, like pick any path on the tree, I can write it as some, like any path UV, like obviously UU, I mean UU also technically, but like fine, like any, let's given any two different vertices, I can always break it up into U to LCA and LCA to V, where LCA is the LCA of the two vertices in the centroid tree. Like everybody can, like you guys all understand the proof for that, right? And why that's true. Like it's a simple claim right now, but it's important to understand that. Fine? Everybody's fine with this. So the most important part of this, like what everything around Centroid revolves around, you've managed to decompose the tree into n log n different parts. Like what your Centroid decomposition has actually allowed you to do is it's allowed you to build a data structure where you've computed n log n different path ka values, and these values are such that the concatenation of any two different paths from this set is like, sorry, any path on this tree, right? Any possible path on this tree can be represented as a concatenation of two different paths from this set, right? The set over here that I'm talking about is a set of n log n paths that you've managed to compute. Fine. I'll talk about what the set is later, but essentially, I'm just letting you know. Like I haven't explained this. It's fine if you don't get this yet. I've essentially telling you that Centroid has allowed you to build this cool thing where any path on this tree, any path, like remember how many possible paths are there in a tree? Order n square, right? Like I mean, depends on order to unordered, but basically you have around n square paths on the tree. But you have managed to build a data structure such that any of these n square paths can be represented as the merger of two of these n log n paths. Fine. If that doesn't make sense, just give me a little bit of time. Cool. What do I mean here? Let's take this tree and let's look at it, right? So for each centroid, okay. So I'm gonna pick centroid 9, okay. For the centroid 9, okay. There are log n levels, right? We know that there are order log n levels. So for each centroid, what you're going to do, like you're computing some function, okay? Like I said with divide and conquer, there's some function that you're computing, whatever. So let this function just be, f of u to v. Okay, that's f of u to v. Basically computes some associative function on the path from u to v. Okay. Now, what your centroid is going to store, right? This is centroid 9. What he is going to store is he's going to store the value of f of 9 to every child in that centroid tree. Okay, so let's see if I can add a. Yeah, let's just add that. Cool. So for 9, so his children are 10, 13, 10, 13, 11, 12, 14, 15, right? 11, 12, 14, 15. So what, so this centroid 9, right? 9 is our centroid. This guy is the centroid. And what he's going to store is he's going to store the value of f of u to v for all of these values. F of 9 to 10, f of 9 to 13, f of 9 to 11, f of 9 to 12, f of 9 to 14, and f of 9 to 15. And yeah, sure, he stores the value of f of 9 to 9 as well, right? So this is what our centroid is going to store. Looking at the centroid tree, he is going to store the value of all the paths that start at the centroid and end in each one of the vertices below him in the centroid tree. Fine. If I store this sort of data for each centroid in the tree, how many, like in total, how many values would I be storing? Right? Why is it n log n? Huh? Yeah. Right. Nice, cleaner than what I had in mind. Yeah, that's cleaner than what I had in mind also. Yeah. So for the proof for that is basically for every node. Yeah, that's a nice proof. So for every node, it has at most log n ancestors. So this value of, if you look at it the other way around, the function from v to the centroid, it will contribute to at most n log n such centroid. I mean, there'll be at most log n centroids for each endpoint. So there will be at max n log n such values that you end up pre-computing, right? The proof is fair for everyone. Everybody understands that. So you have computed this value of f of u to be. Now look at what's cool. We mentioned that in the centroid tree, you can break any path, right? You can break any path f of a to b into f of a to c to b, where c is the LCM of centroid tree. So let's go back to our old example of f of what is it? 1 and 5 was our old example, right? I hope 1 and 5. So 1 and 5 in the tree is going to be 1 and 5. Who's the LCM in the centroid tree? 2, right? So pick 2. Remember, what does 2 contain? When you computed this stuff, 2 has stored the value of f of 2 to 1 and the value of f of 2 to 5, right? So when you want to compute the value of f of 1 to 5, how will you compute it? All you have to do is just merge. Like I said, the function has to be mergeable. The same thing is with the same thing as with segment trace, basically, right? You basically just apply f of 2 to 1. It's a bad place to write it, but essentially you can do something like f of 2 to 1. This value is pre-computed, and f of 2 to 5 is also pre-computed. So given that these guys are pre-computed, you can easily query any path on the tree as the merger of two different paths, right? That makes sense to everyone? This is basically the crux, by the way, of the centroid tree. Everything that we solve basically revolves around the fact that any path on the tree is representable as this, and it's both ways. Like as in, if there exists some path on the tree, it can be represented as a merger, and if there is a if there's, I can also merge any two paths into a complete path, basically, right? If there's anybody to what any, like even if a little bit of this doesn't make sense, ask me now, because this is the most important part that you need to know about centroid. Cool. So let's go and solve problems. Like everybody makes, like it makes sense to everybody, right? Like the whole implementation part of it, I'll get to later. Like if you're worried about like how you're gonna delete edges, do weird bullshit, like we'll get to that later. For now, let's just solve fixed length paths 1, which is oh man, I need to log. Fine, let's solve this now and then I'll screen share on laptop, I think. Fine. So the problem is fairly simple. Given a tree of n nodes, count the number of distinct paths that consist of exactly k edges. By the way, a trend that you might see with centroid is like whenever you see a problem, okay, not whenever, but very often when you see a problem that says, I'm giving you some function and count all the distinct paths on the tree that satisfy that function, very likely that it's solvable with centroid. So, I mean, anyways, let's solve this problem. You can solve this problem a lot easier, but let's solve this with centroid. Okay? How would you solve this with centroid? Right? So these are the values you have. So how would you try to solve this problem with centroid? Huh? Oh, I've done this. Some minutes. Okay, so you get this tree. Yeah, sorry. So you get this tree then. Huh. Right. Right. Yeah. Yeah. So essentially, remember, this contains the value of 2 to 1, 2 to 1, 4 to 4, and 5 to 5. Right. So during the decomposition itself, right, what you can do is basically when you're at the node 3, you've computed all of these values, right? 3 to 3, 3 to 2, 3 to 4, 3 to 5, etc. Also, sorry, the problem asks for exactly k, right? Okay, cool. So all you really need to do is you've computed. Okay, so you're at node 3, right? Let's think about how the DFS goes to compute the the function here, by the way, is just the number of edges on the path, like just standard DFS thing. So, okay, you DFS into, and remember, by the way, very important thing. So, when I say DFS from node 3, it's not on the centroid. It's not on the centroid tree. You are doing the DFS on the actual tree. So the value of f of 3 to 2 is 1, right? The DFS happens on the centroid tree for computing the values, right? All the f of centroid to v values happen on the actual tree. You compute them on the actual tree, right? That might be confusing, so just get that like clear. You're building a different data structure, you're building a different tree, but the values you're computing are obviously they have to be on the actual tree, not on the centroid tree. So yeah, given f of 3 to 2, f of 3 to 1, whatever. So you do the DFS here, you do the DFS there. That tells you that in this subtree you have some, like in this particular subtree, you have some guy with length 1 and length 2, right? So probably like a frequency array is enough, like 1, length 2 is 1, 3 is 0, like frequency array type thing. So when you do the DFS into 4, you have now discovered that, okay, there exists one guy over here with length 1, right? So let's say k is equal to 2. So to that frequency array that you've accumulated so far, you're just looking at, okay, in this DFS, the length over here is 1. You're looking for k minus, you're looking for k minus 1. Like any other node that I've managed to do a DFS from 3 to, that has a value of k minus my current depth equal to that, all of those are valid paths, right? So all you have to do is just sum that up, right? Does that make sense? Like how I'm solving this at centered? It's the same idea with like if you remember this problem, right? You guys remember this problem like Petier and array? Like all we had to do is just do prefix sum, suffix sum, and then for every prefix sum we just check the suffix sum on DNC and you just counted the was it counting the whatever, like the same idea, right? You kept doing your prefix sum on the left side and you used the suffix sum that you computed on the right left side to essentially just count the sum or like do some computation, right? It's the exact same thing with the centroid. Cool. Does that make sense? Like, okay, how many people like aren't sure about it? Like, how many people just don't understand it? Do you guys understand? Do you or do you not? Cool. It's fine. It's fine. So that's the whole idea. The whole idea is just from each centroid, compute the value of some function. The function you're doing is just the number of edges on the path. Have that computed. Then when you're doing the next DFS, just check the computed information. The same thing as we did in the previous DNC forms. So obviously the difficult part or the hard, annoying part at centroid is implementing it. And I mentioned I would put a ping when the like more difficult stuff was being covered. So I will just put that ping right now. Okay. So, like, does anyone have any doubts or anything? Just take like a couple of minutes, I guess. Even if you want to ask like generic stuff. Yeah. Right. So okay. Yeah. Yeah. Fine. Yeah. I think I'll show that during the implementation part. But yeah, essentially, basically asked how do you efficiently compute the value of f of centroid to every node, like while doing it, and it's basically during the construction, right? So. Is a good image to do this. So when the centroid tree is being constructed, right? Like when you took out 8, right? Like I said, like you took out 8 to be that guy in the centroid tree. You do a DFS from 8 to the entire tree, Okay. So while doing that DFS, you incrementally just compute your function, right? Like you have computed f of 8 to 5, 8 to this guy, 8 to this, 8 to this, 8 to this. Like that way you just store those values, right? You've stored those values, fine. Now, what's the next step in the centroid decomposition part? You delete this edge, right? This edge gets deleted. So now when you go to the next centroid, which is node 2 and node 9 over there, what you're essentially doing is you're again going to do a DFS from node 2 to every other node in that tree, right? So go there, go there, go there, go there, there and there. You won't take that edge. That edge won't be taken because it's deleted. Yeah, run DFS at every step, and that is going to be n log n because of what Pratham said. Because remember that DFS, its ending point, can contribute at max to the centroid log n times. So that's basically how you compute the data structure stuff fast. Fine, let's go on to implementation. I'll probably start screen sharing from laptop to show this. But essentially, this used to be my old implementation. Like, by the way, just go for it. Tell me how you think you'd implement this. Like, just what ideas do you have to implement Centroid? Like, I think one of the naive things that you might come up with is change the adjacency list representation from vector vector int to vector set int, right? So yeah, so if you have a vector set int, now you can start deleting vertices, but now you have an extra log n because of the adjacency list being a set. Huh? Yeah, and set sucks. Like in terms of constant factor, set has an extremely high constant factor, so it's a very very bad way of doing it. So a slightly better way of doing it, and what I used to do before is, so you define this struct called edge, right? You keep a edge struct, and it has this boolean value called deleted. I should probably switch to white now. Yeah, you have this value called deleted, which is essentially a marker. It's basically lazy deletion. So in this in the decompose function over there, at some point I'll basically say, yeah, I'll basically set deleted over there to true, and basically amortization bullshit, it'll work, whatever. But this is still extremely inefficient because one, look at the size of the code, it's huge. Also, another very annoying thing you'll notice when doing Centroid is that at each stage of decompose, you need to compute subtree size, which is annoying as it is, and then on top of that, you need to do second DFS to compute Centroid. Like you cannot combining computing, like once you've decomposed into a new tree, you have to recompute subtree sizes, right? You can't even merge computing subtree sizes and finding the Centroid. It's very annoying. Like you have to write two different DFSs. Annoying. Other annoying things, just a lot of code. It's just very ugly. New implementation. That's it. Huh? Yeah, but you need to compute subtree sizes beforehand, right? No, but you don't know the subtree sizes, right? As soon as it goes, uh, as soon as it goes above n by 2. Yeah, that makes sense. Yeah, I think that might make sense. Okay, you can combine them. I think not 100%. Yeah, but I think that would work. So fine, but still extremely ugly. And the fact is, you're keeping a vector of edges basically, and that's not very cache friendly because you have a random boolean over there. I mean, even if you store as an int, whatever, it's not cache friendly. You're iterating over deleted vertices, and probably the most annoying part, in every single DFS, you have to do that check. You have to check that if it's deleted, skip it, right? Bad for branch prediction, bad for all of that stuff. And like, even if you forget all the constant factor bullshit, it's kind of annoying because, let's say you're team coding or something, and somebody else writes a DFS and they forget to skip it. It's not very easy to debug centroid problems because you're working on a different tree while doing a DFS on a different tree. It's not the easiest thing to debug, and if you miss like a stupid like skipping condition, it is pretty bad. So, voila, new implementation. All credits to Oversolver on Codeforces. This was his initial implementation. I did very few modifications to it. I think one of my modifications was adding this level thing over there, and I made the variables like names that I would actually type. I think, but like most credits to Oversolver. I'll show the implementation. I'll just go over it really quickly on desktop. Give me a second. Uh, let's see, meet. Wait, let's just try to screenshot. Right. Let's just. Yep. So this is the implementation of Centroid that I use. So we'll go over this fairly. How do I say? So okay, the top part is basically just simple. So decompose is called on the actual tree, right? And you're given a lambda, right? So how many people here are not comfortable with lambdas? Just use lambdas. Like, fine, just forget it. Just think about lambda, something cool. Like, by the way, like I would highly recommend just look up lambdas. They might look scary, but like you will get over them like very fast. Like it takes like 2 minutes to actually figure out what it does. After that, everything else is just syntactic sugar basically. But essentially, I'm passing a function. Right? Just think of a lambda as a function. To the function decompose, I'm giving it the adjacency list, and I'm giving it a function called. This order over here is basically just BFS order, and like I just do some fancy things. But the cool thing that you need to know is basically you can find the centroid and update the subtree sizes by doing rerouting, right? So after you decompose the top centroid, when you're doing centroid finding on the left subtree, you're basically just rerouting it. Like you can update the subtree sizes on the fly by just rerouting, and that's what this piece of code does. Right? This loop right here, right? So in my DFS function, which is doing all of that decomposition, these three lines basically does both centroid finding, subtree size updating. Yeah, it basically does both of them in just 3 lines. Very clean, iterative, reasonable, like pretty fast as well, right? And my favorite part of this is that the centroid tree is being built bottom up, right? So until now, the centroid tree was like we always talked about it as removing the topmost vertex. Like you remove the centroid vertex, and then you recurse onto the subtree below, right? Now we're going to do it differently. We're going to build it bottom up. So you're going to start with all singleton nodes, and then you're going to combine them, like you're going to add the edges to the top centroid, right? What this change does from going from like going from top down to bottom up is that you don't have to delete edges anymore, right? Because when you do a DFS from any centroid, you've only added the edges to the nodes in that centroid subtree, right? Does that make sense? There is no more need for any kind of deletion because you're working on a separate copy of the adjacency list, which you're building bottom up. Because it's being built bottom up, no need to do any deletions, no need to do any bullshit. You just have a clean adjacency list on which you do a DFS. Is that fine? So this decomposition function, just do that rerouting stuff, and over here, right? This is the bottom down. This is where I do the bottom up part. I first do the DFS. I DFS down to all my children, make sure that all my children's subtrees are built up properly. Then I add the edge, right? From the current centroid to all the nodes, to all the future, what do you say, tree centroids. Fine. So after this, when I call f, what f is the function that you are going to write, right? In my opinion, like Oversolver as well describe this as his perfect API, and I have to agree because it's insanely clean to write centroid code with this, like insanely clean. So I just call like the function that I pass in, right, is called on the centroid tree. And remember, the centroid tree has only been built up so far that no edge there needs to be deleted. So you have all the edges you need in that centroid tree that you're being passed over here. You're passed the centroid and the level, and that's basically everything you need to know to do it. So let's solve that CSCS problem. Fixed length. It is fixed length paths one, right? I hope. So if you look at the code for it, it passes reasonably fast. No even 0.99s and stuff on CSCS. I think CSCS has like tight TL for Centroid over here probably. But this, or maybe for, it might be for path query too, but fine, right? This is all the code. This is all template, right? Remember, decompose all of this is just template. If you're in an ICPC style contest, you never have to care about that. That's just copied from the notebook as template. You only have to write this much. This is the entirety of the code. So this is, what do you say, input reading. We're not even going to count that. The part of the centroid that you're working with is just that much, right? So like I said, we needed a frequency array depth for our solution, right? Answer is basically just keeping track of all the number of parts that do stuff. So to decompose is the function over here, right? So we have passed it the adjacency list, right? Which is the first argument. The second argument is a lambda, right? Which is basically a function. So our solution is basically this function. And you can ignore all of this as basically just syntactic sugar for the function taking in arguments. It takes in the current adjacency list, which is the centroid tree until that point. The centroid, which is the root, right? The root of the centroid tree that we have so far, the size of the centroid tree that we have so far, and the centroid level, right? So when you're at the centroid, what do you have to do? We said we have to do a DFS from there and solve the problem, right? So what do you do here? Let's look at a cleanish way to implement it. Remember, you are at some centroid, and from that centroid to each of your children, you're going to do a DFS. So when you go to the left chart, you're going to say, okay, fill this guy up. Like, you have a frequency array, right? You have to first you have to increment everybody in the frequency array. Fine? Wait, do you not understand this? Wait, no, actually, do you understand this part? Fine, okay. So from the centroid, you increment the value to all the nodes in the first child, right? It's a frequency array. All you're doing is just incrementing is the frequency array, right? So now, if you're not incrementing, right, the second part of it is basically the query portion, where you say, okay, let me go down into the subtree and let me figure out how many other paths end in this centroid, end in my current centroid, such that k minus my prefix value is equal to, the prefix value I've stored so far minus plus my current depth is equal to k, right? K is the length that you want it to be equal to. And that's basically it. So you do one DFS. I wrote it in a single DFS where if it's filling, like I just kept a Boolean order. If it's filling, it updates the frequency count. If it's not, right? That's basically the entirety of this function, nothing else. And finally, I just clear up I need to clear up the depth array, which I've utilized so far. So I just clear it. That is basically the entire thing so far. Does that kind of make sense? And like, I would say if it doesn't make sense right now, take your time, but definitely like appreciate this code and take some time to like go through that code. This is by far one of the best ways to implement centroid decomposition. I don't think you can come up with anything better than this. So it's a very, very nice way to implement. Everything is concise and like kept in a single space, and you don't need to, the whole centroid portion of it is kind of abstracted from you. That said, I will get back to, I'll just stop screen sharing from desktop. So, right. So just for you guys to like sort of go over that problem one more time, right? Remember, when I remove this centroid in the tray, right? If you didn't understand it, if you don't understand some part of it so far, I'll just try to re-explain some part of it. So if this is the centroid, and you've computed the path length till here, right? You're gonna increment the frequency array. Say that there is one guy at depth 1, one guy at depth 2, and when you go over here, you're basically just checking. For this subtree, you're solving for the left subtree over here, right? For this subtree. and there's 2 people at depth 2 and 1 guy at depth 1, right? So you've solved for everybody in this subtree. Remember, for the path merging to happen, one of the paths comes from this subtree, and the other path must come from the other subtree, right? So like I don't care about like this path and this path. Like I mean like I don't care about the yellow path and the blue path come merged. That makes sense, right? I only care about paths that come from T1 that utilize this edge and utilize the T2 edge, right? Only these paths are things that I care about. Fine. That's why we, like when you're solving at the centroid, you use your compute function on this subtree, on this subtree, on this subtree. So you solve the left subtree first, store its information in some data structure, go into the second subtree. Before you put the information in the data structure, just use the information in the data structure you've accumulated so far to compute whatever you're computing. And then store this guy's value in a data structure as well. Go to the next guy. Make sense? So some problems, how long has the meet gone so far? Almost 2 hours, right? So I wanted to cover like Xenia entry and palindromes in a tree. We'll see if we have time, we'll get to this later. I'm not going to go into depth regarding them right now. So I would say try out palindromes in a tree. Screw digit tree, like just don't bother with that problem. It's implementation cancer. Like it's just horrible. Like any problem with Centroid is relatively implementation heavy, but digit tree just makes it even worse. So if you want to go on implementation hellhole, then go for digit tree. Palindromes in a tree, just attempt it. It's basically just the whole idea of centroid decomposition implemented again. Xenio and tree is something cool. You have queries involved. So I'll come back to Xenio and tree towards the end after we do auxiliary trees. Right? So if you have time, we can get to that towards the end. Right now, I'll just quickly go through auxiliary trees. It's not very difficult. Like if you lost track of stuff during the whole centroid discussion, auxiliary tree should be fairly easy. Also, credits once again to Radoslav Dimitrov. He has a video on his YouTube channel, like a very, very nice, nicely explained video. That's where I learned auxiliary trees from. So if you're not watching it live, go ahead and just watch his video. It's a lot better, and I'm basically just sort of doing the same thing. So new toy problem. You're given a tree with n nodes, 1e5 nodes, and q queries of the form ki a1 a, like you're given k is the number of vertices, and then you're given a subset of vertices, right? A1 to aki is just some subset of vertices. You must tell me the pairwise sum of distances between all vertices in that subset. Does the problem statement make sense to everyone? And also very important, sum of ki less than equal to 1e5. Cool? Huh? Yeah, you can do this with square root as well. Yeah, more or less that. So for now, for this problem, consider this tree over here. The special vertices that I'm going to give you are labeled as alphabets. It's going to be X, Y, and Z, right? These are the 3 vertices I'm giving you. I'm giving you, your query is 3 X, Y, Z. You have to tell me the pairwise distance sum between all pairs of these vertices. So essentially the sum between X to Z, X to Y, and Y to Z, right? You have to compute the pairwise sum between them. So as Pratham said, there is a solution with square root decomposition. If the value of ki is like greater than the root n, you can solve it in OFN, and you'll have at most root n values that are greater than the root n, because sum of ki is bound by this thing. Like if you know square root decomposition, it's easy enough to come up with a solution, but we're not going to focus on that solution for now. We're going to try to solve this faster in n log n. Sorry, n log k, I guess, something, whatever, k log k per query basically. But yeah. Yeah, any ideas how you might try to solve this faster than root n? The whole idea here is that you can be linear on the subset that's given to you, right? So you're given A1, A2 to AK, you can iterate on all of these vertices. That's not an issue, because the sum of Ki is bound to be under 1E5, right? So you can just iterate on each of these vertices. So, I mean, because the name of the meet is also, auxiliary tree, By the way, auxiliary tree goes under multiple names. I've heard the name auxiliary tree, virtual tree, compressed tree, whatever. Like people use a lot of different names for it. I think the most popular one is auxiliary tree and virtual tree. But like, yeah, fine. Just a heads up, I guess. So the whole idea here is to create a new tree, an auxiliary tree, so to speak, that works out pretty well. So tell me this, right? Let's suppose you could construct a tree where you inserted all the LCAs between all pairs of vertices. How would that look like? So for this tree, we're given vertices x, y, and z. What are all the pairs of LCAs between all of these vertices? Huh? 5 and 5 and 5 and yeah, 0, right? Right, 5 and 0. So if I had inserted all the LCAs between all pairs of vertices in this in my special subset, right? Granted, k square, k square is possibly in all pairs of vertices. I do k square insertions. What is cool about the tree now? Like, what can you do with this new structure? Any idea? Like now that I've inserted all k square LCAs, what is something cool that you can do? Like, what has happened to the tree? Or rather, what can you do now to build sort of an auxiliary tree that you couldn't when you didn't have the LCAs? Okay, if you don't get it, basically what you can do is you can build a tree using straight edges. You can just directly connect these guys using edges and you get a new tree. You don't like it's a direct edge. And what is cool about this edge is it's just the composition of these two edges. So remember, before this we had an unweighted tree, so the weight of each edge was just 1, 1, 1, 1, 1. Now what you get is a weighted edge, right? So the distance from 0 to 5 is 2. From 5 to this is 2, 1, 2, right? 2, 2, 2, 1, right? So you've basically just inserting k-square LCs allows you to build a new tree where you can add edges between the LC and like you can just add edges in the normal order of DFS such that like you don't need any more vertices to build a proper tree, right? Like if this vertex 5 wasn't there, you had no nice way of connecting Z and Y. But now that the LC is there, you can just connect them with an edge, and the edge is just the weighted accumulation of like the edges on that path, right? That is basically what the auxiliary tree is. So why is this important? Like, why is this cool? Like, anyways, I have to do k-square insertions, like k-square LCAs, right? Like, what the hell is the point of this? Is that you actually don't have to. You will have at most order O of k vertices. Even if you considered all k-square LCA, all k-square vertices ka LCA, the total number of vertices that you'll add will be at max k minus 1. Oh, for what? Wait, you took a meet in supernotree? You covered supernotree and square root decomposition? Fine. Yeah. So, yeah. Why is it order O of k? Once, fuck. I thought I was charging. One sec. Shit. Well, technical difficulties. It's not charging. One sec. It's not charging. Why the fuck?
So like worst case you can keep it there.
No, one second. Just give me 1 sec. Let me see what the state is. Still discharging, bro. How? Oh, it's charging. Look. Yeah, fine. That's fine, right? Okay. So we'll just give a quick proof for like why there will be at max order of k vertices, right? So mm, wait, 1 sec. So okay, so no, I haven't even told how you insert it, right? So we need to come up with an order of insertion that will give us at max order k minus 1 insertions. What I will claim is that order the tree by DFS order, right? So take the tree and just order it by DFS order. So you get 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Right? So in this case, our vertices were these guys, right? Y, Z, and X. I will claim that sort the vertices by DFS order. So you will get Y, Z, and X. Only insert the LCA of adjacent vertices in this set. Right? Only Y and Z and X. Fine. So the LCA of Y and Z is 5. I'll probably mark that in like blue or something. And the LCA of Z and X is 0, right? So we only insert these vertices in the set. So how many LCA insertions am I making? K minus 1, right? So I'll claim that these 2k minus 1 insertions are sufficient to have all n square possible LCAs. Fine. Why is this true? So let me claim that these guys don't have it, right? That means, okay, so let's pick any arbitrary node u and some node v in the tree, right? And let's try to say that if I did those 2k minus 1 insertions, his LCA must be in this set, right? So the LCA of these guys is going to be some node x, okay? That's u, that's v. He's going to have some LCA x, fine? What we know for a fact is that node U and node V are not right after each other in DFS order, right? Like that means there is some node in this DFS order that occurs between U and V, right? That much is known. So fine. Let's do this. Consider this entire subtree, right? There is some subtree of node X that leads towards node U, right? Like node X will have some subtree that goes towards node U. So find the node with the last DFS time in that subtree. Let this be subtree T1. Find the node with the last DFS time in the subtree, right? Let it be node A, fine? This is our cool node, and eventually it connects back to node X. Now, between node U and node V, there must have been at least one node, right? In DFS order, right? Remember, if that isn't the case, that if there is no other node outside of the subtree of T1, that no, so uh, either A is the node, and then right after that I visit node V, right, in DFS order. In which case I would have put the LCA X, right. The other case is that there is some other node in some other subtree, right, which I end up visiting before I end up visiting B. I cannot exit the subtree of X and visit some other guy, right? Because in DFS order, I must have either A was the last node and then I visited node V, in which case I inserted the LCA X into my collection. Otherwise, there must be some other subtree in which I visited some guy. But if I take the LCA of node A, and that's some other node, right? The first other node that happens in DFS order between U and V, I would have again inserted X for sure, right? These are basically all the possible cases. No matter what, you would have ended up inserting all the k-square like all k-square pairwise nodes ka LCA if you did that sort by DFS order and insert adjacent nodes ka LCA into the set. This would have accounted for all of them, right? So this basically just lets you do auxiliary trees. Like you've managed to build a new tree on top of which like the only like any technique you know to solve problems on trees so far, ATT, HLD, square root trees, sorry, not square root trees, like whatever, square root decomposition, Moz, no, maybe not Moz, but yeah, fine. What else? Centroid, uh, anything else that you can really think of, anything that you can solve on a tree in nlog n, you now have a new tree in the form of k vertices that you can solve in k log k on, or like k root k, or whatever you want to, right? So that's really all auxiliary tree is. It's built you a new tree on which you can apply any tree technique that you know to solve, like any technique you know to solve problems on a tree, tree DP, whatever it is, you can apply it on a tree that has only order k vertices. That is basically the entire appeal of of auxiliary tree. So my implementations use Cactal, so I'm using KCTL's implementations. So this top half is basically asking for RMQ and LCA. So this is basically O of 1 LCA, the top half. That's what it's importing. I'll sort of quickly go over my auxiliary tree implementation. Cactal's LCA already computes the DFS time. So my timer T over there basically is just a reference to the LCA structure's DFS time. Uh, Nothing very fancy. There's a comparator basically to sort by DFS time. I'm just sorting the subset by DFS time, and then I insert all the adjacent vertices LCA into a set, and then I uniquify them. So I might have inserted the same LCA twice. Let me just unique it. If you like, one way to unique, like make an array of elements unique is to throw them into a set and then put it back into an array again. But a much faster way of doing it is just sorting it and then calling unique. Like the standard library has a function called unique that will just do it for you. Now the only like somewhat nice like cool part of doing this, like you want to avoid an extra log factor, so you can do it with a stack. What this basically does is like remember all your nodes are sorted in DFS order, right? So when you're building your auxiliary tree, like let's say you've managed to build the auxiliary tree up till this point over here so far. So let's say the last node you inserted was this guy. Now you come and insert a new node over here, right? The LCA might act, and you would have visited the LCA in DFS order before you actually come to him. So this guy must have also been on the stack, right? But when you come to this guy, let's say the last node on the, wait, I think that's not a good example. So yeah, there's a node here which needs to connect directly here, okay? But in your stack, you end up pushing this guy first, 2, 3, 4. So now when you're adding this node 5, he has to directly connect to node 1. So all you do is you just keep popping back from the stack. And because it's all in DFS order, your stack has been populated in DFS order, you can just pop 4, 3, 2 until you reach a node that is an ancestor of me. Then you just add the edge between those guys, and then you push 5 onto the stack. It's basically the monotonic stack type thing to basically like remove a log factor. Just try to convince yourself why it works. Just remember that it's mainly because you're populating the stack in DFS order. You can just do the linear time reversals and get it. That's my implementation of auxiliary tree. Uh, what? Okay, I had a problem called kingdom and cities. It looks like a hard problem, but in fact, so this problem, by the way, is I think rated like 2800. With auxiliary tree, it's very trivial. I mean, it's a small edge case, I guess, but like it's extremely trivial. It's not worth being rated 2800. But auxiliary tree is often. I mean, this is an old contest as well, I think, so that could be a reason for inflated rating. But I mean, just read the problem once. Essentially, you're given a tree with n nodes, n minus 1 edges, and you're given queries basically, right? Each query is a set of vertices. The king wants to know what is the minimum number of vertices that there are these bandits. Like these bandits can, so the king gives you important vertices, and he wants to know if I shut down, like bandits can basically shut down any vertex that's not important, right? So what is the minimum number of vertices that the bandits have to shut down so that there is no direct connect, so that there is no path that passes through safe vertices between any two pair of vertices that the king gave you. Just read the statement once if that isn't clear. Is that clear? The statement's clear, right? Okay. So, I mean, if you looked at it, given any two vertices, so let's imagine there's another slide here, but like if the king gave you some, actually let's just go back to that old one. So if the king gave you those red vertices, right? For a bandit, if you look at it from the point of view of the bandit, it's always optimal to attack at the LCA of two adjacent guys, right? Because like this might not be the easiest thing to prove, but the like if I give any number of vertices over here, you want to delay, like, okay, let's say there exists a path between a vertex A and B. You want to delay blocking it as high up as you can. And ultimately, you'll be forced to block it off at one of those K-square LCS, right? That makes sense, right? So the bandits will end up blocking all the LCS. And now you have, like, that's minimal, that's the optimal answer for the bandit. But there's also cases like this where yeah, pretty much, yeah. So let's say the king gave that guy and that's this guy. The bandit cannot actually block off the red node. Like he can't block off the parent. Like whatever nodes the king gave, the bandit can't block off. So like here, you cannot delay it till you. You have to kill it. You have to kill the node just below, no matter what. You're forced to do this. Huh? No, one child is enough. You, yeah, just one child is enough, right? So this also naturally gives you an impossible case, and the impossible case is basically where, yeah, the king gives you adjacent vertices, in which case, no matter what the bandits do, they just cannot do it. So the solution for this problem ends up being a little bit of like DP casework on the auxiliary tree. Also, fun fact, another reason why auxiliary tree problems aren't very common is that, you know, it's very telltale, right? Like you look at the input query format, you just see query K and then a set of nodes. Like you're always given a subset of nodes. That does not imply that the problem, like given a query format like that, doesn't imply that it's an auxiliary tree problem. But very often you'll notice this. Like I think very recently there was, I think, a CF from I sold. Yeah, it was a recent. I mean, I can't say recent, but okay. Something related to rerouting instead. But like, fine. Like it's often the case that like when you're given input like that, reasonable that auxiliary tree might be the solution. So that's why supernode trees are kind of cool because they combine the square root decomposition idea with supernode trees. So like I won't go into any depth about supernode trees at all because the meet's already taken this long. Like let's just say that given a tree, let me pick all the nodes that are at a height of root n from the child. Okay. If I pick these, okay, let me first pick all nodes that are height root n from leaves, and let me remove these subtrees from the tree, and then set the height of the node above that as 0, and continue this process. Okay. If you remember, this was basically in the Indian Amritapuri preliminary round. This was Amritapuri preliminary round 2022, I think. Right? We had second solve in India because I watched this video, I think, like the night before the contest. But I mean, it's a very similar construction. Like the problem basically told, given a graph, find root n nodes such that no node is root n distance away from it. So that was basically the problem. And essentially, this construction, find a spanning tree and just pick nodes at height, root, and works. So let's just say you found a way to pick exactly root and special nodes from a tree. You build an auxiliary tree on these root and nodes. The number of nodes in this new tree structure is still order root n. Now you basically can compress, like you have this special tree where each edge is actually some compressed thing, right? Like I'm drawing something that looks like resistors right now, but like each edge is basically a compression of a bunch of nodes, like around root 10 nodes, right? That's this structure that you've managed to compute. So now querying any path on the tree can be done square root style by just jumping blocks like that and then doing root the standard square root stuff, but you can do it on a tree basically. That's what a supernode tree is, and it's for path square root stuff. Very cool structure. You can look at it. There's this cancerous problem called May holidays. It's a Div 1E on CF. I think only a double LGM team solved this in contest. Like their implementation is cancerous. I hope it doesn't need to reach that. From what I remember, it was really, really bad. I don't think it needs to be that bad, but a pretty cool. And I think you can solve it without a supernode tree as well, by the way. But the constant factor I had trying to solve it without supernode tree was insanely high. Like with a supernode tree, it's just much nicer, much easier to solve it. Like by much nicer, I mean it's still horrible, but much better than the alternative. But that is basically what auxiliary tree is. It's this cool idea that lets you do whatever you want with it. How long has the meet taken? 2.5 hours. Yeah, I think I'll be stopping the meet now. Like, I think the only real problem I wanted to kind of show is Xenia entry because it involves using Centroid as a, what do I say? As a querying structure. I'll just sort of mention what the problem is. Like, I'm not going to go into detail. We'll just finish up the meet in like five minutes or so. Just read the problem once. You're given a tree, and you have queries of two forms. Paint a blue vertex red, and calculate which red node is the closest to a given vertex. Fine. So initially, all the vertices are what? Yeah, all the vertices are red, and they're given queries of two forms. One, paint a node blue, and the other, wait, no, what the hell? Sorry, all the nodes are initially painted blue, my bad. All the nodes are painted blue, and now you basically just have to answer queries of the form. Either update a vertex's color from blue to red, otherwise answer what's the closest vertex to me that's red, right? So if you remember the centroid structure that we have, right? Remember, centroid isn't just used for like counting the number of paths. The tree structure itself is a queryable structure. What I mean by that is, look at this centroid structure, right? So at every centroid, when I color a node red, like let's say I'm coloring this node red, right? Let me update the distance to this node. This node is node 6, right? So what is the distance from 6 to 1? Sorry. 6 to 7, sorry. What's the distance from 6 to 7? 1, right? So the minimum distance from this node to any other node is 1. What's the minimum distance from 2 to 7? 3. Yeah. So to each of the parent centroids, I'm going to update that, okay, from this centroid, the closest distance to a red node, I'm just updating that distance, right? Like you can find the distance between two nodes in like O of 1. I hope that's known. Like path distance between two nodes you can do using LCA. Like you can do that on O of 1. So like given, like whenever I paint a node red, I just have to update my centroid parents that, okay, I am a new red node, I might be closer to you. So just update the minimum distance from each centroid node to each node. And when I give a query at a node, remember any path from that ends at that query node, like let this be the query node, this is the query node Q. Any path that ends at query node Q and ends at any other vertex can be represented as Q to one of the centroids, and from that centroid to some other vertex. I don't care what that is, but the centroid is stored. Remember, the centroid C1, C2, and C3. Each centroid is storing the minimum distance from that centroid to some other red node. So all I have to do is just min the distance between distance from Ci to Q plus f of Ci, right? The centroid is storing the minimum distance from the centroid to every other red node. So I just go to each of my login centroids and just sum it up and take them in, right? So you can do queries at centroid also. Like I've solved problems where like you have to like update LR range queries. Like you can put a segment tree into like the centroid ranges, put T in T out, do all sorts of weird shit with it. So very very cool, powerful data structure. Sort of sucks that like it becomes very recognizable and a problem is solvable by centroid and auxiliary tree, but at the same time they help you solve like very difficult problems. Like, these are not problems that would be easily solvable if like these ideas weren't there. Especially just introducing divide and conquer to a tree is a fairly difficult task that centroid lets you do. So yeah, that's basically the entire meet. If anybody has any doubts, do ask me right now. But yeah, that's it. I'll be ending the meet here. Any feedback, anyone? How is it? Fine. Cool. So yeah, I will be ending the meet then. Oh hi Arpan. I'll text you I guess. But yeah, cool. Yeah. Bye guys. Thank you for attending. And I'm ending stream.